the objective for experiment 4 is to determine the equilibrium constant of a keto-enol tautomerization. So let's look at a case of acetone, the 3 carbon, and the carbonyl group in the center carbon. At the room temperature, there is equilibrium between this keto form and this enol form. I label this hydrogen as red. So one acetone undergo this reaction, goes to enol form, this hydrogen transferred to the oxygen. Okay, so basically just move that hydrogen here, so the double bonds move from carbon-oxygen to carbon-carbon. In this lab, we're going to look at the equilibrium constant based on the definition of equilibrium constant. That will be the enol concentration divided by the keto concentration. Okay, if I write the equation this way, right? And at the room temperature, because this structure is a lot more stable than the enol form, so and the room temperature is almost, if you can look at the percentage of the keto form, it's almost all molecules are in keto form, and a very small, very tiny fraction is in the enol form. If we look at the other molecules, so for example, if we look at this one, this is you count carbons 1, 2, 3, 4, 5, and that's number 2, number 4. So this is a 2,4 pentadiene, and this is an example of beta dicarbonyl compound. So this is the alpha carbon, and this is a beta carbon. And the beta carbon, that's a carbonyl, and it has 2 carbonyl group. This is the keto form of that compound. And what happens if this compound undergo a keto-enol tautomerization process? One of the hydrogen moved to oxygen, right? The carbon-oxygen double bonds move to carbon-carbon. From this form, it can switch to this one when the hydrogen goes to this oxygen, and or to that one when the center hydrogen move to the right oxygen. Okay, so if you look at the minus log K value, it's 8.9, there is significant part of the enol form exists. Okay, so matter of fact, this is only 24% of the molecules remain in keto form, and other molecules are in enol forms. This is because when the beta dicarbonyl compounds form an enol form, that forms a 6-member ring here. So that make the ring structure relatively stable, so they can stay in this way much longer than the enol form of acetone. And this is important, especially in biochemistry, because if you look at the DNA structure, there are a lot of enol keto tautomization there. So this is this is a guanine, and this is thymine. These are the elements for DNA. And if you look at the structure here, this particular structure here, it's an enol form, right? And here it can transfer to a keto form. So why this enol form is stable is because when it forms the enol form, it actually forms aromatic ring with adjacent carbon and nitrogen. Okay, this is an aromatic structure. It's very similar as benzene, except there are 2 nitrogens in the ring. And you can see there are 3 double bonds separated by 1 single band. This structure is very important in a lot of biological systems. And why do we want to use the proton NMR, and what they should be look like? here I use this molecule as an example. So this is the alpha carbon, and this is the beta carbon. This is a beta dicarbonyl compound, right? Agree? And then it should undergo tautomerization, become this enol form. I label each hydrogen place with a different color. So these two methyl group are in light blue, and these two methyl group are in black, because they are really far away from the carbonyl groups. So their chemical shift, the methyl group should be very similar. So I label here, the larger peak is methyl hydrogen from compound 1, and the black peak, can you see that shoulder there? There's a small shoulder, that's the methyl hydrogen from compound 1A. So I want you guys to pay attention to this one. So this one is really far from rest of the peaks. What's this one? This is the hydrogen from the OH group, because this hydrogen is so close to the oxygen. So the chemical shift is much larger than the rest of the other hydrogens. So usually you can easily identify this peak because it's so separated from the rest of the peaks, okay? And so on and so forth. So we can identify this one as the alpha carbon hydrogen in the enol form. And this one is the alpha carbon hydrogen in the keto form. How do we calculate the equilibrium constant based on this? We know the peak intensity is related to the concentration of a compound. The peak intensity means the area that's covered under each peak. And in the TopSpin or SpinWorks software I ask you guys to download in our first lecture, that software can help you identify the area under each peak. Once you have that information, because each peak represents the concentration of that particular hydrogen, then you can add all the keto hydrogen together and add all the enol hydrogen together and take the ratio of that area. And basically, that's the ratio of the concentration. And then you can get the equilibrium constant. So what about this one? Can you see this one? I labeled all other peaks, right? I labeled all the hydrogen peaks from the compound. What about this one? I didn't label anything here. That's the solvent peak. That's the peak from this deuterated chloroform. You're going to have a different solvent, and you're going to see the solvent peak at a different shift. So in your spectrum, you need to figure out, okay, what solvent is used. I'll tell you the solvent, and then you need to figure out where the solvent peak is and make sure you don't count the solvent peak as your keto or enol peaks. The other question is, if you look at the methyl groups, okay, look at these two peaks, light blue and the black. And basically, these two peaks are overlapping. How do you tell this area of each peak? So I mean, when you do the peak area calculation, for example, you calculation the pink one, it's really easy, right? You click here and click there, they'll give you all the area in between. And for this peak, where do you go? You click. I mean, you can't get where the black peak tails off at. So what do you do with this one? You have two ways in terms of solving the overlapping peaks. One would be similar as what I did here. So I do the integration twice, the calculation twice. So first time I would click here, and the second time I would I would take a guess where the peak should end, and I'll probably click somewhere there, and they'll give me a number. Then I will erase that calculation, erase that peak, and calculate again for the other larger peak. But usually that will give you very large errors because really you don't know where the peak ends or starts. The other way would be just, we use other hydrogens. The problem of using smaller number of hydrogens is that when the number of hydrogens are smaller, it usually comes with larger arrows because you only rely on a small fraction of the hydrogens. So what I would recommend is in this case, if you look at the light blue and the black hydrogens, the number of hydrogens are the same, right? 3 plus 3, that's 6. 3 plus 3, that's 6. And you can use the rest of the other hydrogens because then the rest of other hydrogens should be the same, right? So in this case, I would use green and the pink to represent the keto form. And in this case, I would use, in the eno form, I would use the yellow, blue, and the red to representing the eno form.